Hey everybody, Dr. Boyle here. Hope you're all having a good start to your second week of the semester. Today I'm going to be lecturing about rocks, minerals, kind of how they form, the different types we have, and it's a lot to go over in one lecture, but we have to get it done, so let's get started. Okay, wow, that locks. Okay, cool. So, Chapter 2, Rock Forming Minerals and Rocks. So the guiding questions today, we're going to kind of look at what are minerals, kind of what determines their physical properties, and kind of how they're bonded and structured. Then we're going to look at what sorts of conditions produces various types of igneous rocks. Again, remember these are the rocks that form from a molten liquid. And then we're going to look at different types of sedimentary rocks and how they form, and then also how metamorphic rocks come into being. For minerals, we're going to look at structures of minerals, properties of minerals, and then we'll get into the types of rocks. But more basically, let's start with looking at just kind of the basic building block of a mineral, which is an atom or a molecule. Remember, atoms are made up of protons, neutrons, and electrons. And the protons and neutrons are housed in the nucleus here. And then the electrons orbit that nucleus. Electrons have a negative charge, and protons have a positive charge, which causes the attraction there. Now, this is a more simplified view of the atom. Okay, so this is kind of that, high school Bohr model of the atom, or whatever you like. But more realistically, atoms are housed in these probability clouds. Don't worry about this. I just want to show you how complicated real life is. We like to boil things down in science classes to these really simple explanations, but life is super complex. And so in a really simple model, you have a cloud around us, a single nucleus, and there could be any part of that sphere, the electron could exist at any given time. And it's called a probability cloud. And they get more complicated the more complicated the nucleus gets, so on and so forth. So you can see you get these really weird geometries, and I think they're kind of pretty to look at. It's also really mind-boggling to think that our world is made up of these little atoms, and the electrons are spinning around so fast, and they could exist in these locations, or there's a 90% probability that they exist in these locations, and it's all very mind-boggling. But it's cool too that such complexity can lead to the things that we have around us. So an atom, again, it's made up of it has a assigned atomic number. That atomic number is unique, and it's equivalent to the number of protons. So oxygen, for instance, has 8 protons, and in its normal state has 8 electrons. And the atomic weight of any given element is the number of protons plus the neutrons. So as long as nothing else has gone wrong, okay, there should be an equal number of protons and neutrons. So oxygen with 8 protons should also have 8 neutrons, giving it an atomic weight of 16. And silica, or silicon, 14 protons should have 14 neutrons, giving it an atomic weight of 28. Now, real life is, again, more complex than that. We get things called isotopes. And isotopes have different atomic weights, but of the same element. So keeping the number of protons the same, all right, so these all have 6 protons. These are all carbon. All right, we have carbon 12, carbon 13, and carbon 14. So remember, protons are staying the same. Atomic weight is the combination of protons plus neutrons. So that means that our number of neutrons has to change. So carbon 12 has 6 protons and 6 neutrons. Carbon 13, 6 protons, 7 neutrons. Carbon 14, 6 protons, 8 neutrons. So this is that kind of, and remember, this is the stable state here. This is where the atom kind of wants to be eventually. So if you have a lot of excess carbon 14 in something, it will want to decay back to something different, right? And so one of these neutrons is going to shoot up out of there and decay back. And so this is kind of how radiometric age dating works. I won't get too much into it, but this is the stable state, this is the unstable state, and then this is created due to cosmic ray bombardment in the atmosphere and some other stuff. So again, very complex. Don't worry about too much. If you want to go on and take more higher level courses about this stuff, they are available. Anyways, so just know that isotopes behave differently in the environment, but they behave similarly as far as chemistry goes. They'll basically have all the same chemical properties. But let's say, for instance, you have a bunch of water. And in that water, you have, water is H2O, right? So 2 hydrogens, 1 oxygen. But oxygen has a bunch of different isotopes. So let's say you have a bunch of oxygen that has an atomic weight of 16 versus a bunch of oxygen with atomic weight of 18, and different water molecules are evaporating. Well, water molecules with oxygen 16 will be favored to evaporate because they're lighter. And then water molecules with oxygen 18 will stay behind because they're heavier. So these things actually allow us to track a lot of natural processes. So isotopes are super important, and they allow us to track a lot of things. Again, not super important for this course, but we will use them to help explain kind of how we know stuff. Okay, so a lot of people like to ask, like, how do you know this happened? How do you know this happened? Well, it's mostly because of isotopes, especially when it comes to age dating. But the science behind that is pretty complex and is kind of hard to explain with due diligence in an intro course. You need a whole extra classes and sometimes even entire graduate programs to understand some of this stuff. So chemical bonding. This one I struggled with when I was younger. Why do something like chlorine, for instance, okay, why does chlorine want to gain an electron? Or, why does sodium want to give up an electron? Why does that happen? And it has to do with the fact that an extra electron in an orbital is an unfavored state. Okay, they either want to be all full, half full, or empty. And this has to do with there being an energy state change going from an empty to all full orbitals. And if that doesn't make sense, think about it like this. You were climbing a mountain and you had different stops on the mountain, each of them having like a bed and some place to rest and good food. And you're walking up that mountain and you make it to one of those places, and then you go a little further and then you're like, oh man, it's still another 3 hours to the next location. It's getting dark, I'm cold, I'm tired. I don't know if I want to make it all the way to that location. I'd rather drop back to this location where I can rest and have food and get rested. And so that's what you choose to do, right? Because that's the lowest energy state for you. You might require a little bit of backtracking, but it's way better than having to go all the way to that next location. And so that's kind of how this works. It's a lower energy state for sodium to give up an electron than it is to gain, 7 more electrons, okay? Because there's only the number of protons to have that 1 electron. So it'd rather just get rid of that electron, enter that lower energy state, and be happy. And so thus it gains a positive 1 charge. Chlorine, on the other hand, is just 1 short, okay? You're just below that next rest stop when you're climbing that mountain and you're like, oh man, I know I can make it. And you get up there, and that's, you're really happy that you put in that little bit of extra effort to get there. So naturally, when chlorine, which needs 1 more electron to become a stable energy state, and sodium, which wants to give up 1 electron to become a stable energy state, meet, they enter what we call an ionic bond, where one atom loses an electron to another atom, and they attract like this. And ionic bonds are not that strong, they're easy to break. So that brings us to our definition of an ion. An ion is a charged atom, okay, either positive or negative. A cation is a positive charge, okay, remember cats have paws, positive, and then anion is just the other one. So that's dumb. I don't know why I still do that. I learned that in 7th grade and I still do it. So cations are positive, and anions are negative. Yeah. Okay, so in covalent bonding, remember electron, one atom's giving up an electron, so you got electron donor, and this is an electron acceptor. Okay, well in covalent bonding, you don't need a donor and an acceptor. These electrons are actually being shared, so the bonding's a lot stronger. Okay, you're not just like, here's an electron, thanks, bye. You know, they're actually being, they're shared and they're more tightly bonded. This happens a lot of times in half-filled orbitals. So like carbon, for instance, there's 4 electrons in its outer shell, and it wants 8, and so it sees another carbon, and that carbon also only has 4, and it wants 8. So they kind of start sharing. They each share their electrons with the other to satisfy their outer bonds, and that makes them very strongly bonded. And this example here is diamond. Diamond is just pure carbon. Tightly compacted and bound together. Yeah, but there's also graphite's pure carbon, and it's not very strong at all. So it's interesting how you can have 2 different things that are both made of the same elements but have completely different physical properties, and that has to do with their mineral structure. So on to mineral structure. So this idea of crystal lattice, it's a 3D molecular structure of a mineral. In salt, for instance, remember going back to that ionic bond, sodium and chloride, okay? Salt is, or in geology we call salt halite, H-A-L-I-T-E. And so halite is just pure chlorine and sodium, and it's in this kind of cubic structure. And remember, ionic bonds are really easy to break. So when you smash salt, it breaks into cubes. And so these sodium chloride bonds form little cubes. Even down to the atomic scale, they form little cubes. And so every time you break salt, it's always going to break into these like nice 90-degree angles. And so that desire to break along angles like that, we call that cleavage. Okay, so you see this here, this is cleavage planes. It's like, so you're cleaving this thing along a plane. And it's an atomic weakness on which it breaks. Okay, so that's what cleavage is. So we're going to talk about that here in a second. I want you to know that it's referring to the atomic weakness in the mineral that causes it to break along predefined surfaces. Okay, and not every mineral has cleavage. Okay, but that's just kind of the idea here. So remember, crystal lattice is all the way down to an atomic scale. For instance, some minerals may have the same chemical composition but appear very different. Just like the diamond and graphite example, you also have things like calcite, aragonite, limestone. Okay, so these are all the same chemistry. Right? They all are calcium carbonate, but they have very different chemical or different mineral structures because of the way that they formed on the Earth. Okay, so this brings us into the definition of a mineral. And a mineral is defined by being naturally occurring. Okay, so it means it can't be made by humans. It can't be, artificially made. So it's naturally occurring. It's inorganic. And what inorganic means is that it doesn't contain organic carbon. Okay, so like coal, all right, coal would not be a mineral because that contains organic carbon. It doesn't mean that it's, I don't know, like doesn't come from an organic farm or something. That's not what it talks. Inorganic purely just refers to the fact that that it has if it has carbon in it, it can't be organic carbon. It's a solid. It can't be like a gel or a paste. It has a definite but not fixed chemistry. And so why this is important is because what you'll see in a second is that a similar mineral can change quite drastically in its appearance based off substitution of trace elements. And by trace elements, I mean one element in a million. Okay, so if we go back to this here, one of these sodiums could be potassium in a million. One in every 1 million sodiums could be potassium, all right, and it would still be halite, all right, so it doesn't have to be definite, all right, so, or it doesn't have to be fixed, okay, it doesn't have to be an exact sodium chloride all the way through. It can have a little bit of different changes here and there. So it has a definite but not fixed chemistry, and then it has a crystalline structure, which we already kind of talked about. So that kind of brings us into a fun example. We have glacier ice here and an ice cube with, I guess, apple juice to keep this family friendly. And so the glacier ice here, let's run through our definition. Naturally occurring, yes. It's inorganic. There's no organic carbon in there. It's just H2O. It's a solid. It has a definite but not fixed chemistry, right? So there might be a little bit of debris in there, like dirt or dust, but it's still mostly fixed chemistry of H2O, and has a crystalline structure, which ice does. Ice has a really nice crystalline structure. And so then, ice in nature is a mineral. But what about ice cube that was made in our freezer? It fits these 4 down here. However, it's not naturally occurring because we made it in our freezer. So that tells you, like, if you make ice in your freezer at home, it's not a mineral, it's an artificial mineral, right? But if you see ice out on, forming as an icicle in the winter on a rooftop, then that would be technically a mineral. And depending on how big it gets, a very dangerous mineral. Some more examples of that. All of these minerals here are the mineral plagioclase. It's a type of feldspar. It has the general structure of calcium, aluminum, and silica, and oxygen. Okay, pretty simple. There's only 4 elements that make this up. However, by changing the ratio or by substituting a little bit of sodium in for the calcium, you can drastically change how it appears. In this one down here, we've actually substituted potassium for the calcium, and so it changes how it appears. So this is all a mineral feldspar, and these are different versions of that feldspar. And you can see how different they look. In fact, labradorite is actually one of my favorite minerals. And it has this cool, when you get the right ratio of everything, it has this cool thing called labradorescence. And it gives it this blue sheen. Yeah, it's kind of showing up on the camera. Getting too much reflection from the window. I don't know if I can stop that. Okay, but you can kind of see how there's a blue sheen in it. Oh, there it goes, yeah. But yeah, so labradorite's really cool. One of my favorite minerals. And, but yeah, it's really simple. It's just calcium, aluminum, silica, and oxygen. But they happen to come together in the right way to form a crystal lattice that reflects and refracts the light in a certain way that gives you this really cool, shiny labradorescence character. Onward. So different minerals have different properties, and they have hardness. So this is actually how strongly the minerals kind of bound together, and we test hardness by actually taking the mineral and scraping it against different things. So like pencil lead, for instance, you're not going to be able to scratch glass with pencil lead, right? But if you took a diamond and rubbed it on glass, you're going to scratch it very easily, right? So that hardness is how we test things. And there's a thing called Mohs hardness scale, and you'll look at this in your lab too. But it runs from 1 to 10, with graphite kind of being the softest 1, diamond being the hardest 10, and then you have a whole range of things in between. That mineral feldspar that I was just showing you, that has a hardness of about 6. A steel nail has a hardness of about 5, 5.5. Glass has a hardness of about 6, 6 or 7. It depends on the glass. Our Gorilla Glass on our phones, that has a hardness of about 8. Okay, so it's a little harder to scratch. That's why your keys generally won't scratch it unless you have cheap glass or really hard keys. And then a penny, the copper coating on the penny, has a hardness of about 3. Our fingernails are about 2.5. So that's kind of some ideas, and you'll get into this when you get to your lab. Okay, so and then density, mass per volume. So I have a couple examples here. So this is a mineral. So online learning is interesting sometimes, but this is a mineral called galena. And you can see it actually has that kind of cubic-y structure to it. Okay, it looks very cubic-y. This is super dense. This is actually a lead sulfide. Okay, there's tons of lead in here, and lead is a very dense element, and thus leads to a very dense mineral. Like this here, this little small piece here probably weighs like 5 pounds. All right, so it's super dense. Yeah, you wouldn't want to get hit in the head with this little thing. Whereas then I also have a piece of obsidian, roughly the same size, all right, but pretty light. Like I would probably get hit in the head with this and be mad, but not dead. You know what I mean? Like it's like, okay, well, it's But and this is basically just silica. It's like 75% silica with a bunch of other stuff, because it's a glass, so it's actually not even a mineral. It's amorphous. But just so you got some ideas. But density is kind of like how much of a heavy stuff is in a certain volume. And a lot of this has to do with the chemistry, okay, and also the packing geometry. Diamonds are more dense than graphite, even though they're the exact same chemistry. So how you pack everything in there is going to play a big role, but a lot of it's controlled by what elements actually make up that certain mineral. So, okay, so that's density. And next is fracture. Remember, we talked about earlier with salt breaking along those predetermined planes of weakness at the atomic scale. That's called cleavage. Okay, well, just like that galena I just showed you, that also has that cubic cleavage. Well, things can also just fracture. Quartz, for instance, when you break quartz, it also fractures like glass almost. Okay. And we call that conchoidal fracture. There's all sorts of different ways minerals can break, and you'll learn about them in your lab. And you won't learn about everything, but if you go on to take another upper level course, you'll learn about more and more of these complex ways things kind of happen in nature. And just kind of to round out the mineral properties, just know that the composition of a mineral and also its internal structure are very indicative of how it formed in nature. Okay, where diamonds have that really nice compact structure, and they're pure carbon. Okay, they form very deep within the earth in the mantle, where high pressures cause that carbon to form in these super tight packing geometries. Whereas graphite, still pure carbon, forms up more in the crust. Okay, it's still under high pressure, but it's not anywhere near the pressure of diamond, and thus you don't get these super nice packing geometries. And carbon, therefore, is super soft, not expensive, whereas diamonds are super hard and probably artificially expensive. They're more common than you think. Diamond companies just have a monopoly over everything. So there's way more rare minerals you could make a ring out of and have it be a lot more meaningful. Okay. Okay, so mineral types. So there's probably like 10 different kind of mineral groups. Or types, I should say. For this lecture, we're just going to go over a few. You have silicates, carbonates, sulfates, oxides, and native elements. And so the silicates are predominantly made of silica, and they are formed of silicate tetrahedra. And a silicate tetrahedra is 4 oxygen atoms surrounding. Sorry, that's a typo. Whoops. 4 oxygen atoms surrounding 1 silica atom. So and essentially it forms these little kind of nifty, kind of triangular looking, or well, tetrahedra looking things. And yeah, so and then these little guys here will actually bond together to form different geometries. So they can form chains or sheets. For an instance, when they form a sheet, you get things like clays or micas. And you may have seen mica before or played with it when you were a kid or even when you're an adult like me. But it's this mineral that kind of peels off really nicely in really thin layers. And every time you're peeling those layers apart, you're actually breaking the bonds between these different sheets of silicate chains. And I think you have some in your lab kits, but I can't remember if you do or not. And I haven't received my lab kit yet to confirm that, because there's a back order. Because everybody's online now. So, but we're gonna make it work. Don't worry. Okay, so carbonates. These are formed by a cation bonding with a carbonate complex anion, and the CO3 2- is the carbonate anion. And then usually it's calcium, magnesium, iron. There's some other ones too, but some positive ion will bond to that. Okay. So this is an example of dogtooth calcite. And this forms in aqueous solutions, and it's really pretty. And so that's purely just calcium carbonate, CaCO3. And then dolomite, really similar. It just, instead of just CaCO3, half of this calcium is replaced by magnesium. Carbonates are kind of what make up a majority of the rocks that form in the ocean. Some other just minerals, sulfates, that galena I showed you, that big cubic guy, that's a sulfate, lead sulfate. They form at low temperatures generally via come out of aqueous solutions or hot water. And by low temperatures, it's still like hot enough to where we would probably not be happy if we were touching it. It wouldn't be good for us, but it's good for these minerals, and it's way colder than, like I say, a magmatic temperature. And then oxides are all sorts of things like rust, hematite, Fe2O3. Magnetite can form in magmas, and these form kind of all over the spectrum of things. And so oxides are really important for ores. And then you also have native elements like gold and copper and things like that that will also come out of solutions. And so if the sulfates, the oxides, and the native elements, those are all kind of under this category of like economic geology. All right, so just know that those things exist, and that's also a field you can go into. Okay, so into the rock cycle. So I briefly introduced in the last lecture this rock cycle, that any rock can turn into any other rock at any given point in time, given enough time and the right conditions on the planet. So an igneous rock can cool, and through weathering and erosion can turn into sediment. That sediment can be deposited, and that turns into sedimentary rock. If it becomes lithified, you can then bury it and heat it up and turn it into a metamorphic rock. You could melt that and turn it back into magma. This metamorphic rock could itself turn into sediment, go back to sedimentary rock, etc. So there's this whole rock cycle. And it's something you want to familiarize yourself with. I don't think it's too hard to memorize. 3 rock types in sediment, and then, and just kind of the different ways you can go in between each step. It makes a lot of sense once you start just kind of thinking about the planet and how it behaves. So igneous rocks are purely classified by their composition, so what they're made out of chemically, and their grain size. Composition-wise, you have felsic and mafic. Felsic means it has a lot of lighter elements, okay, both in color and in density, or lighter minerals. Mafic means it has more dense elements and dense chemistry. It's also darker because of that. Well, it's darker because the dense minerals are dark, which is just convenient for us. So felsic rocks are things like granite and rhyolite. That's these bottom two. I think last week I showed you examples of granite and rhyolite and how they're very similar in color but super different in texture, and that's because of cooling rate. And so if you cool something rapidly, it becomes very fine-grained, and the term we use for that is aphanitic. Okay, aphanitic means that you don't see very many crystals, okay, or any crystals at all. And if you cool something very slowly, you get large crystals. We call it large grain, and that's phaneritic. So aphanitic, phaneritic. There's also something in between called porphyritic, where you have large crystals and small crystals. And what that means is that it was cooling slowly, and you were getting big crystals, but then all of a sudden it was erupted and then cooled really quickly. So cooling history plays a big role in what you see in igneous rocks and composition thing through something called Bowen's reaction series. And Bowen's reaction series, okay, from very simple, is that if you take a body of a melted rock, and you cool it very slowly, different minerals will come out of solution at different times, okay? So, for instance, if you take the basalt, like in the Columbia River flood basalts that you see in eastern Washington, and if you take that up to a really high temperature and melt it and start to cool it very slowly, I'm talking really slowly, like hundreds of years, very, very, very slowly, then the first thing that, as you're cooling it from high temperatures, so say you have it at 1400 degrees Celsius, as you start cooling it, when you hit about 1200 degrees Celsius, a mineral called olivine starts to precipitate. And then as you continue to cool very, very slowly, eventually you hit a point where calcium-rich feldspar, that plagioclase, okay, that starts to precipitate. And then pyroxene starts to precipitate, and then amphibole, and then biotite, and then so on and so forth until you get down to this feldspar and muscovite and quartz. Well, what this does then is it affects kind of a distillation. You're freezing out things that want to cool, and then the leftover liquids become enriched in these things that haven't crystallized. So if you take an ultramafic rock and you cool it down to here, all right, everything left over is going to be stuff that would want to be an intermediate or felsic rock. So you can actually create felsic rocks by slowly cooling ultramafic or mafic rocks. And then if you do that enough, you can build up a ton of this felsic material, and then that can then, you know, melt and then move around as well. So this is kind of like Bowen's reaction series, distillation, a thing called fractional crystallization. And so you can take something very primitive, or, you know, super ultramafic, we call this primitive, and you can evolve it to a point of this felsic by just fractionally crystallizing and distilling off that liquid. And I think that's important to understand, that a volcano like the Hawaii volcanoes that erupt purely basalt, if you stall that basalt out in the crust a bit and cool it, you can actually remove more felsic material from that, and then you can get a more mafic, or you can get more mafic stuff left behind and more felsic stuff erupted. So like the Cascade volcanoes, those are all erupting things that are super felsic. And that's because the crust there is so thick that the basalts that are coming up and feeding the kind of the root systems of these volcanoes, they're stalling out, they're cooling, and that leftover felsic liquid is kind of working its way up and then erupting. And so there's a compositional control on physical properties, okay? So these really mafic volcanoes, they are super low viscosity, all right? So this is like an example of a Hawaii volcano in here. You can see how this lava just really flows smoothly, kind of like a thin oil. And then as you thicken up, you're becoming more felsic, okay? So felsic rocks are actually more viscous, and they resist flow. Remember, the viscosity is the resistance to flow. So things with really high viscosity don't want to flow very much, okay? So like this here is getting very viscous. These here are barely even starting to drip out. So this would be super high viscosity, and this is super low viscosity. And this is honey, just honey being poured, and I just think it looks pretty, and it shows kind of a lower to medium viscosity, but not like water, right? Water flows a lot more easily than that. And then this is a basalt lava, lower viscosity, and this here is actually a dacitic lava. Okay, this is a felsic lava, and it actually it flows so slowly is that it kind of forms these domes that kind of just fall, but it's still a liquid. It's just so high viscosity that with our eyes we don't really see it as a liquid. We kind of see it as a solid, even though it does flow like a liquid, which is kind of hard to imagine, right? Something so viscous that it's still a liquid, it just happens to flow so slowly that our eyes perceive it as a solid. So on the kind of the concept of igneous rocks, so when magma cools inside the earth, we call it an intrusive igneous rock. We talked about that last week. And then at the surface, we call it an extrusive igneous rock. And magma is inside the earth and lava is on the surface. So we call it lava, magma. So, and then for intrusions, intrusions are very slow cooling. That's where you get your big crystals. Remember that term phaneritic, okay? So intrusions cool very slowly, and these form things called sills and dikes, or plutons. Pluton's kind of the bigger one. A sill forms kind of horizontally to the rock layers, and then a dike cross-cuts vertically the rock layers. And so those are the terms we use. Again, remember at the surface, we have lava. And remember, the magma's inside, lava's outside. Lava is a molten rock that appears at the vent. So this here is a cool lava flow, and you can see how like flowy and liquidy this looked. And then a tuff, we call it loose volcanic debris, but a lot of those more viscous silica-rich felsic rocks are going to be forming your tuffs. And then, but you also see some kind of tough material here, but this is mostly just a flow. And then fissures are kind of like horizontal or elongated cracks what lava flows out of. And then if you have these lava flows build up over time and your fissure becomes a more centralized vent, we can then start to call that a volcano. These are just some examples of some stuff you can see in Washington. So flood basalts, they're basically this super liquidy material flowed out from big centralized vents for a long period of time, and you covered the whole landscape in basalt. So this is an example of a flood basalt. You can see the layers. in each one of these layers is probably an individual flow. But this is a lot of material coming out of the earth. It's kind of impressive to think about. And if this comes out underwater, then you can form these things called pillow basalts. And this is due to basalt rapidly cooling under the ocean. Just another more cool examples. Again, when you get into geology and it becomes super complex at the higher levels, and there's so much to know and see that we witness happening on the earth, and each of these things is like evidence of some natural process occurring. Okay, moving on to sedimentary rocks. So sediments are produced by basically the weathering and erosion of other rocks. And other sedimentary rocks are produced by precipitation of minerals from seawater. And you can also produce it by skeletal debris. So all of these rocks kind of have that same thing in common, where you're taking something, you're making a grain of it, and then it's settling out a solution, or precipitating out a solution. But the point is that it's happening on the surface of the planet. So siliciclastic rocks are sedimentary rocks composed of a class of other silicate minerals. And they don't always have to be pure silicate minerals. Obviously, you can have some oxides in there and stuff too, but quartz and feldspar are kind of your two most things resistant to weathering, and thus they are the most stable, and so they're more stable on the planet, whereas things like olivine, those mafic minerals, are less stable. And I don't know if you remember, so think back real quick to that Bowen's reaction series of how olivine was the first to come out, and then plagioclase, and then, amphibole and stuff. Well, the reverse is true for what's most stable on the surface. So olivine is the first thing to weather out on the surface because it's actually most stable at high temperatures, right? It's really stable at that 1200 degrees Celsius. So once on the surface of the planet, it's like, I don't want to be here. I'd rather not, and so it dissolves away. Whereas quartz forms really a lot lower temperature. Quartz forms down in at the 600 to 700 degrees mark, and so it's much more happy just on the surface of the planet. It's also got a more kind of simple, stable structure. It's got these really long, complex silica chains that make it hard to dissolve. But generally, that's how you think about it. Things that are low on Bowen's reaction series are also most stable on the surface of the planet. Oh, and this is called the Goldic dissolution series. You don't need to know that. I just wanted to explain that. Okay. So sedimentary rocks, the siliciclastic rocks, that is, we can split into grain size. So things with really, really fine grain, we call, things that are made of clay. These are going to turn into clay stones or shales or mudstones or siltstones. Mudstone is kind of the general category of siltstone, claystone, and shales. And it's basically all things that we would see on the surface and be like, hey, that's mud. All right. If it got wet, if the dirt got wet and turned to mud, we'd call that mud. And that's kind of what a mudstone is. When you start to see and feel the grains, though, we then call that a sand. And then if that lithifies, that's a sandstone. And then when you see gravel, like a gravel bed, like in a river or something, or the playground, I guess, if you're still going to playgrounds. Well, if you have kids, you probably are still going to playgrounds. Well, maybe not during COVID, but anyway, so if you see gravel, if gravel becomes lithified, then it turns into a conglomerate or breccia. And remember, lithification is just the process of gluing everything together. And you can do that through a whole suite of different things. And it happens pretty easily in nature. Just that kind of, all the grains become glued together. And that's lithification. Okay, so again, this classification is based off grain size and shape, and these are all the different classifications. So gravel has, granules and pebbles and cobbles and boulders and anything bigger than 2 millimeters in diameter, which you can maybe visualize. A conglomerate is a lithified gravel of rounded grains, and a breccia is a lithified gravel of angular grains. And then you get into more of these classifications. Remember, sand, often quartz and feldspar, and this turns into a sandstone. These are your size determinations. Silt and clay, so on and so forth. And these become super complex. Again, everything becomes complex when you look at it in more detail. And I just want to show you this USGS grain classification chart. And so here's the size terms. So you can go very fine silt, medium silt, coarse silt, very fine sand, medium sand, coarse sand, so on and so forth, to where your brain might explode. But it's out there, and if you ever got into the science of actually studying sedimentary rocks, these are things the way you would classify things. So continuing on siliciclastic rocks, an interesting thing about the muds and stuff like that is that muds are formed of really fine-grained flakes of clay, and they're elongated. Remember, we talked about the silicate minerals, and I said that those silicate chains can form sheets. Well, these are an example of that. So in large flake of clay, right? Okay, well, this is actually a sheet of those silicate minerals, or those silicate chains, sorry. And in solution, when a flake settles, it likes to settle flat. They tend to fall flat, okay? And that's because if it lands on its edge, it'll kind of fall flat. And what that happens is, over time, if those compact, you actually get this kind of fissile texture. It's like everything's kind of aligned in one direction. And if that becomes lithified, you can form, in like really hard, you can form something called shale. And shales are like these super hard, super fissile, we call it has like slaty cleavage. That means it kind of breaks off in like flakes. And so it's actually breaking along its bedding surface. And so this can actually tell us a lot about original horizontality, all right? So if we find one of these shales in the field and we see all of its flakes are dipping like this, that means that it was originally deposited like this and then tilted, okay? So this is important for understanding the history of a rock. Sorting. So sorting is also important, and what sorting can tell you is kind of like depositional direction. Okay, so this is a way up indicator, or we call them geopedal structures. So it's things that tell you which direction was primarily up at the time of deposition. And what happens is if you take a bunch of sediment in a bottle and you shake it up of various grain sizes, and then you let it sit, all the super heavy things settle out first, and super light things kind of stay in suspension and then settle down later. And you've probably seen this in the river. If you ever walked around in a river or something, you spread out all the mud kind of comes flying out, and then it makes the water really cloudy, but all the big sediment kind of like easily settles right back down to the bottom. And this is the idea of Stokes settling velocity. So big grains fall easily because there's not a lot of drag versus their weight, whereas small grains, as they fall, they don't have a whole lot of weight, and so the weight to drag ratio is really high. So there's actually a lot of friction from the water keeping that thing in suspension. But it would settle out eventually as long as the water stops moving. So sorting, this is kind of a measure of similarity in grain size. Oh wait, sorry, real quick, I'll back on this. So if you find a rock in the field where you see a bunch of coarse grain stuff grading up into fine, well then this is probably an example of where, this was the original up indicator. So you can tell if a bed has been flipped all the way over or not. So sorting, this is kind of a measure of similarity in grain size. So you can go from very well sorted to very poorly sorted. Poorly sorted is kind of like mixed stuff where you have like sands mixed with gravel, and well sorted is where you have just primarily sands. And this has to do with energy of deposition. So really high energy events will take everything that doesn't discriminate. So big flooding events and stuff will just kind of pick up everything and deposit it, whereas like lower energy, just regular flow or wind or something like that will only select certain grain sizes and leave behind others, and so that kind of sorts it out. So a lot of sedimentary rocks, we can kind of make interpretations on the amount of energy at the point of deposition. Rounding, another sedimentary term. Rounding is how smooth the surface of the grain is. So during transport, collisions with other grains. So if you take like these guys here on the far left and they slam into each other, eventually what happens over time is they become more rounded because these angular high surface area portions kind of break off. And so you go from something like this over time during length of transport, so how long this stuff has been moving around together and bumping into each other, it'll go from something like this all the way to like this. So this would be like a super primary grain. This would be like right after it kind of fell off the rock, okay? Right after it was weathered and started to be eroded. And this would be after a long time of transport. Sandstones aren't always just pure sand or pure quartz, which I've kind of already mentioned. You can have also feldspar dominated sandstones, and they'll be kind of pink in color. And greywacke is actually an outdated term, still kind of used, but it's basically a sandstone that has a lot of mud mixed in with it, and then it's been lithified. Okay, so lithification, what I already kind of talked about. Basically, it's where you take loose sediments and they become glued together to form a rock. And this happens in conjunction with compaction. And there's all sorts of ways you can glue things together. You can have calcium carbonate cements, you can have silica cements, you can have iron oxide cements. So there's a lot of ways to glue these things together. Okay, and kind of one of the last things I want to talk about as far as sedimentary rocks are evaporites. And well, not the last, but close to the last. Evaporites, they form from evaporation of water, mostly seawater, and as they evaporate, different elements become concentrated in the water, and eventually become so concentrated that it becomes saturated or then supersaturated with respect to certain minerals forming, and thus these minerals will then precipitate, and you get them. So halite, gypsum, anhydrite. So all of our salt that we have came from large evaporite beds. So the salt that you eat and stuff like that. Especially like the Himalayan sea salts, stuff like that pink salt that has become very popular. That has a lot of potassium in it, and that's what gives it its kind of pink color. Anyway, so they form pretty easily, and they all dissolve pretty easily in water. And so a few other ones, you have chert, flint, and banded iron. These all form at the bottom of the ocean. Chert is actually, interestingly enough, when you get to really low levels in the ocean at high pressure and low temperature, silica that's dissolved in the ocean starts to kind of precipitate as this kind of silicic gel, and it forms these amorphous. So amorphous means no crystal structure. So it forms these amorphous kind of extremely small quartz pieces, and we call that chert. And it's actually not even quartz crystals. I shouldn't have said that. But so it's actually more just an amorphous quartz. It can be all sorts of different colors based off impurities. There's blue, chert, and everything else. Flint just means there's a lot of organic material in with it. And flint has this interesting property that if you knock it together with metal, it sparks. And then also at the bottom of the oceans, things called banded iron formations form, and we now get them on the surface. And they're representative of times where before the Earth had a lot of oxygen, we had a lot of dissolved iron in the water, okay, because nothing could oxidize it, so it was dissolved in the water. And then as the planet became more oxygen rich via bacteria producing oxygen, eventually that oxygen became dissolved in water, got into the oceans, and caused this dissolved iron to precipitate, and it precipitated to the bottom of the oceans, and it formed what we now call banded iron formations. And then carbonate rocks, again, these form in the oceans generally. You can get some freshwater carbonates, but mostly these form in the oceans. They're formed of, there's a whole bunch of different types. You can do your entire graduate course. You can do your entire graduate degree basically just looking at one type of carbonate rock. Okay, so they're super complex. There's limestones, and limestone can have fossils in it, or it can also just be fossil free. There's dolomite, which it's more common on the planet for ancient carbonate rocks and not so much for recent ones. Carbonates can form their own sediments, so especially when you get into with skeletal debris. You can have carbonate skeletal sediment rocks, you can have carbonate muds. A lot of the carbonate mud is actually a little worm in animal poop. They digest things and form carbonate mud poop. It's kind of interesting. And then that settles, and yeah. So there's all sorts of different ways you can form these carbonates. And primarily in the oceans today, we form a mineral called aragonite. And that's this aragonite needles here. So, and a majority of this course will be kind of looking at all the different types of fossils we see and how they've been precipitated, and it gets pretty complex, and I won't get into too much here because we'll get into it later. Yeah, and then there's some things called ooloids, or oolites in this case. But so ooids are these little spherical balls that form by a central grain rolling around in the ocean in currents, and then these aragonite needles kind of like precipitating on it. Yeah, so they're pretty cool. You can actually find bunches of these at certain beaches. They almost kind of look like sand, but they're actually carbonate nodules. This is one of those ooloids I was talking about. So these are like sand grains that had rolled around and then precipitated aragonite needles around it. Okay, so again, sedimentary structures. So sedimentary rocks will have structures that are indicative of how it was deposited. And so here's one of those cases of how grading and bedding. So here it's all coarse grained, and here it's fine grained. So you can imagine during this event, all the coarse grained material fell out first, and then finer grained material fell out later, suggesting that the energy of this event decreased going upwards. Okay, so we had high energy to start with, and then it got to low energy at the end. And so you can, this helps you interpret like sort of how these things were deposited. And this would be what we'd call a normal grading. Okay, reverse would be the other way, where starts with small stuff and then works its way up. And it could mean that it was overturned. A lot of times you'll see preserved in the rock record ripples. And so ripples form by wind or water. And you can have symmetrical bidirectional currents where the waves kind of move in and out and in and out, and that causes these rounded edges. But if current only moves in one direction, you get a gentle slope with a steep slope. And what happens is the sand grains kind of work their way up that gentle slope, and then when they hit the backside of this steep slope, they fall very suddenly to the bottom. And the current actually, they're protected by the current, so they're allowed to settle. So this is where all the deposition happens. Here is on this backside. So they kind of like hit the bottom and build their way up, and then hit the bottom and build their way up, and so you can slowly build ripples out this way. And so depending on the energy and the size of the water and stuff, you can get really, really large ripples, or very small ripples. But the current always points in the direction in which this gentle slope increases. So if you see ripples in nature, okay, if you're out and about and you find some ripples in the rock, you can actually figure out which way the water was flowing at that time. And kind of lastly here, we're getting into metamorphic rocks. And metamorphic rocks are kind of a little different because they actually are just the product of altering other types of rocks, right? So either sedimentary or volcanic. And what happens is then the rocks kind of change in their chemical composition, and as far as like what minerals you see. Sometimes chemicals are completely removed with fluids. But the amount of changing and what they change into is dependent on the grade, and this is the temperature of metamorphism. Usually also coupled with pressure, but doesn't have to be. Temperature or grade purely depicts temperature, and so you can have different types of metamorphism. You can have regional metamorphism, or contact metamorphism, or impact metamorphism. Contact would be where a hot rock, like a volcanic rock, comes in contact with a cooler rock, and so that contact surface, you actually get a change in the host rock. due to the heating, but it doesn't have anything to do with pressure. It's just temperature. And regional metamorphism is where you actually increase the temperature and pressure at the same time, and then eventually it comes back to the surface because we see it today. And so this regional metamorphism transforms really deeply buried rocks. And during regional metamorphism, you get something called foliation. And so based off the pressures of metamorphism, all the minerals align in one direction, and that causes this thing called foliation. So it's an alignment of minerals caused by applied pressure. So metamorphic rocks are generally foliated unless it's contact metamorphism or impact metamorphism, which are more rare. But our general, most common type of metamorphism is this regional metamorphism. And so this foliation here, you can see indicated by different grades. So here's a low grade foliation in slate. Okay, so this almost looks like a sedimentary rock, like a shale or something like that. But then as you increase the temperature, all the minerals in here that are super fine grained right now start to become bigger because they've had more time and more temperature to help them reorganize. So they've reorganized into these larger minerals. And then really high grades, really high temperatures, they actually really start to reorganize. It almost starts to look like an igneous rock, like a granite, but it has this defined slatiness. Okay, so we call this a slaty or platy cleavage. So it has this nice, or you can also sometimes call it schistosity. It has this really nice alignment of all the grains, and that's due to pressure. There's other types of minerals that won't align. So marble, which is calcite, or quartzite, which is pure quartz. These actually, their minerals don't align in any kind of long direction, so you won't see that alignment because they just don't align. So they actually just form massive blocks. The way to tell these two apart is to put acid on them. So if you scratch the surface of this and put acid on it, it's made of calcium carbonate, so it'll fizz. Just like all the other carbonates will also fizz when you apply acid to them. In quartzite, if you scratch the surface and put acid to it, it won't fizz because you're not breaking any bonds. So that calcium carbonate ionic bond is easy to break with acid, whereas quartz is a super strong covalent bond, and you can't really break it very easily with a simple acid. You can dissolve it with really complex acids that are dangerous, but we're not going to use those in this course. Like I said, there's different types of metamorphism: contact, hydrothermal, burial, impact. If you have like a meteorite hit the planet, we have those types where you get super high pressure but not very high temperature. Contact metamorphism bakes the surrounding rocks. Hydrothermal, the water alters the rocks. Sometimes we just call this alteration instead of metamorphism. It just depends on what book you read. And then burial metamorphism is that similar to regional metamorphism, where you're burying the rock to a really low point in the crust, and it's becoming a super high temperature and high pressure. One common metamorphic product is coal. This is low-grade metamorphism of plant debris. Remember that coal is not a mineral because it contains organic carbon. But yeah, if you bury coal, or if you bury organic material that hasn't been oxidized, so things that get from a swamp, basically, if that gets buried and put to a high pressure, then you get all this, and it turns into kind of this more pure carbon, and then you can burn it to oxidize it, and that gives us energy and produces CO2, and depending on how dirty the coal is, produces a lot of other bad byproducts. So we don't burn a lot of coal in the U.S. anymore. It's becoming more rare, just because it's bad for the environment, and other energy options are becoming cheaper and more sustainable. Okay, so that kind of wraps up the lecture. And I just want to leave you with this really cool, kind of complex rock cycle. And you can search for this rock cycle illustrated by Phil Stauffer, and this will come up. This is a free download. You can look at it. But it just shows you all these cool, super complex, so in the volcanic realm, right, we have intrusive igneous rocks here, we have extrusive igneous rocks here, we have basalt, rhyolite, dacite, andesite, based off the the type of the Bones reaction series, or the type of rock it is. And basalt generally is more dense, so it sits lower, and andesite and rhyolite are sit higher. And then those can turn into sediment, and depending on the size of the sediment, it's super complex, and I think it's really fun to look at, and I find it pretty accurate, and it's you don't have to know this, obviously. You just need to know the more simple version, but I think it's pretty fun, and it kind of shows you how dynamic and complex the Earth is. And looking at all these things that occur today, we can see this occurring today, and then look at it in rocks from the past, and start to kind of piece our planet together. So these we're gonna consider the building blocks to this class, right? We're gonna find that all these things we're learning about and look at occur today, but they've also occurred in the past, and we're going to use them to try to tease out how the Earth kind of came to be in its current state. Anyways, so that's everything. Remember to get your discussion post done for the geologic timescale, and I will continue to make posts on Blackboard and update you with things that are going on. I think this lecture went a little long, but there's a lot to get over for this one. So yeah, anyways, thanks for tuning in if you watched. And if you didn't, then, well, you're not hearing me, so I guess it doesn't matter. Okay, have a good week, everybody.